For part 2, let's take a look at how we can graph parametrics. Now we want to graph parametrics over the following interval, 0 to 5. And it's kind of fun to do. We just make a table. Except for a different type. It's a little different. We have x. So instead of t, we have our x value and we have our y value. And this time we're going to get a point for an answer. So I want to go from 0 to 5. Well, if I let t be 0, well, my x value is negative 3. My y value is 1. So that's the point 3, 1. Let x be 1. Okay, keep going. This becomes 3 minus 3, which is 3. Y is 2 plus 1 is 3, so it's 3, 3. Let x be, t be 2. This time we get 6 minus 3. Oh, wait, 1, 3. Oh, that should have been 0. My bad. There we go. Sorry about that. Let x be 2. We get 6 minus 3, which is 3. 4 plus 1, which is 5. So we get 3, 5. Go 3. We're going to get, what's that, 6. And 3 get 7. So we get the point 6, 7. Go 4. That becomes 9. 8. Oh, look, 9, 9. 9, 9. Let x be 5, and the last one, 15, we get 12, we get 11. So we get 12, 11. So I'm going to graph all those points. Now, the one thing about parametrics and why we like these in physics is because it's directional. At negative 3, 2, 3, at 1, this is where we're going to start. And I'm going to keep graphing it. The next one's at 0 up 3, 1, 2, 3. And I'm heading to this one, and I'm going to draw an arrow heading towards it. At 3, 5, 1, 2, 3, up 5. I'm going to head up to there. At 6, 7, 1, 2, 3, 4, 5, 6, 7. At 9, 9. There, went out of the room. Right here, and so on and so forth. And at 12, 11, I ran out of the room. There it is, 12, 11. And I get a graph. I don't know what that looks like, but we can kind of figure it out. Let's find out what shape this is. Let's convert this. Now, to convert, we're going to pick one of our variables, preferably the x one to solve for t. So I want to convert by, it's called eliminating the parameter. Eliminate the parameter. And that's what we're going to do right now to convert. So for this x, we get 3t minus 3. Solve for t. We get 3t equals x plus 3. T equals x plus 3 over 3. And I'm going to take this parameter and I'm going to plug it into the second equation. Y equals 2 instead of t, x plus 3 over 3 plus 1. And it's kind of hard to see, but this is actually a line, because watch what I can do. This becomes 2/3 x plus, and I distribute this 2/3 plus 2 plus 1. And we get the line y equals 2/3 x plus 3. So this parametric equation is a line, but it's a different type of line. It starts at only from 0 to 5. So this is the graph of the line with a domain restriction, only going from 0 to 5. And we use this in physics. Where did I start? Where did my end? Very easy to do. So let's take a look at 2. Let's see if we can graph this one here. Pick your variables. We got t, x, and y. This time we go from 0 to 4. 0, 1, 2, 3, 4. And I'm going to plug them in. Plug in 0 here, 2, 0 squared, 0. So I write out my point. This is just a point, 2, 0. Plug in 1, I get 3, 1. Plug in 2, 4, 4. Plug in 3, we get 5, 9. See, to plug in 4, we get 6 and 16. Now notice this one is definitely not going to be a line for us this time. So let's take a look at what happens here. Plug it in. I'm going to give myself a little bit more room. I'm really only working with the first quadrant anyway, so might as well do that. Where do I start? And where do I end? Well, I'm starting at the point 2, 0. From here, I'm going to go to 3, 1, 2, 3, up 1. Draw arrows. The next point, 4, 4. 1, 2, 3, 4. 1, 2, 3, 4. The next one, 5, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Definitely not a line this time. And then 6, whoops, space out a little bit better, 16. It's 9, 10, 11, 12, 13, 14, 15, 16. Wow. So the question is, what shape is this? And it's kind of obvious because if you think about it, we're going to let x equal t plus 2 and we're plugging into something squared. So this is probably a parameter. But before that, let's eliminate the parameter. To do that, I look at the x equals t plus 2. So t will equal x minus 2. And I'm going to plug that into the squared function. So y equals x minus 2 squared. This is a parabola on the domain 0 to 4 only. So nice things about parametric equations, they allow us to have domain restrictions pretty easily. All right, kind of misnumbered this. This should be number 3 and that should be number 4. Let's take a look at something like right here. Let's graph this one. So we got t, x, and y, and a point. All right. This one's not going to be very fun because we're going to go from 0 to pi over 2. Use our values. 0, I know pi over 6, pi over 3. Whoops, let's do pi over 4 first, I guess. Then pi over 3, and then pi over 2. Okay, I use my known values. Now the cosine of 0 is 1, so this becomes 4 minus 1 is 3. The sine is 0, so that's just 3. So that's 0.33. Plug in pi over 6. The cosine of pi over 6 is root 3 over 2. So this is 4 root 3 over 2 minus 1. Ew. Plug in sine. Sine of root pi over 6 is 1/2. So that's negative 2 times a half plus 3. So as a point, 4 root 3 over 2 minus 1. And that's just negative 1 plus 3, 2. Yuck. Plug in pi over 4. That's not too bad. 4 root 2 over 2 minus 1. Negative 2 root 2 over 2 plus 3. So easy to do. This is 2 root 2 minus 1. Negative root 2 plus 3. And we're not going to worry about graphing this one, but we can just get the points here. That'd be pretty easy to do. Okay, so let's go and finish up the points here. Plug in pi over 3. Cosine of pi over 3, that's a nice one. No, sorry, not so nice. That's root 3 over 2. Oops, sorry, that is a nice one. That's 1/2. So this becomes 2 minus 1, which is 1. That's nice. Sine, negative 2 root 3 over 2 plus 3. So this becomes 1 comma negative root 3 plus 3. And plug in the pi over 2. Cosine of pi over 2 is 0. That's just negative 1. Sine of pi over 2 is 1. That's negative 2 plus 3 is 1. So we get negative 1, 1. All right. But that's not what I want to spend the time with. For this one, I want to spend the time with eliminating the parameter here. So if I were to eliminate the parameter, this is different. It has our cosine sine. For this one, I'm going to use my cosine squared of t plus sine squared of t equals 1. So what I'm going to do is I'm going to solve. Let x equal 4 cosine t minus 1, y equal negative 2 sine t plus 3. And I'm going to solve. If I solve for cosine, I get cosine of t equals x plus 1 divided by 4. Do the same thing for sine. We get the sine of t equals y minus 3 divided by negative 2. Ew. Okay? So what I want to do this then is square it. I square the cosine. That's going to give me x plus 1 squared over 16. Whoops, ran out of room there. Over 16 plus, now, the negative here, I should put that on top, okay? If I want to put the top negative on top, I make this 3 minus y over 2. We don't want that bottom there negative mess. Makes a mess for us. this becomes then, if I square this, 3 minus y squared over 4 equals 1. And if you notice, we have an ellipse here. Sometimes it's easier to write the ellipse right here than it is to graph it up here. All right, so let's take a look at the next one, number 4. Now for number 4, let's not worry about getting all the points here. Let's just practice eliminating the parameter. First of all, that should just be 2t, just 2, not 2t. So if I want to eliminate the parameter for this one, we let x equal, now this one should look a little, 3 tangent of t plus 2, y equals the secant of t plus 3. Solve for tangent of t, solve for the trig, x minus 2 over 3. Solve for the secant of t, that is y minus 3. Now, what trig identity are we using here? This is our Pythagorean, and we're going to use a Pythagorean that says secant squared, that tangent squared of t plus 1 equals secant squared of t. So, in other words, if I subtract it, I would get the secant squared of t minus the tangent squared of t. That's going to equal 1. And this is the one I'm going to use. Plug it in. So it says take my secant and square it. So I take this y minus 3, square it, minus my tangent squared, x minus 2 squared over 9, that equals 1. And now the question is, what shape is that? Very good. It's a hyperbola. Now, we haven't had to do part 3 in a while, so go on to part 3 and we'll do the last part, okay? Thank you.